So first we have Suvi Gezari from Space Telescope. Tell us about TDE or not a TDE.
Great, thank you so much. This has been really interesting. And my talk, I want to give you sort of an update on the latest developments in observations of tidal disruption events. We actually now have quite large samples, relatively speaking. So we have about 50 tidal disruption events that we've systematically classified and followed up from the Zwicky Transient Facility survey. So I'll be showing you some of those results. But then obviously in the theme of this workshop, I want us to be thinking in the back of our heads, TDE or not a TDE. That is the question. And I certainly want us to take some of the time in my slot this morning to really ask the question, are QPEs in TDEs or not? You know, what is the evidence, and discuss. And also, you know, I talk about TDEs a lot, but I'm more interested in opening a discussion with you guys. So please feel free to stop me. I also want us together to take a fresh look at some of our observations. Many of the phenomena that you guys have been talking about in the QPEs, I'm noticing some analogs in the TDEs. So let's go ahead and pause and look at the data and see what exciting things that pop up. Okay, so one little piece of family history that I can't not share, which is that Einstein is a very special figure in our family, and in particular, Princeton plays an important role because my grandfather, Suvi Gezari, was an industrial engineer, but a very avid amateur astronomer. And he had heard that Einstein had never looked through a telescope. And actually, I think he came up to he crashed a cocktail party at Princeton because he lived in New York. And I think he even chatted with him and asked if he had ever looked through a telescope, and Einstein said no. So my grandfather said, "Can I build you one?" And Einstein said, "Oh my gosh, you know, I don't know if I could accept such a gift." I mean, he was pretty much a celebrity then, so people were already always kind of offering him things. But my grandfather went ahead and built a telescope and then presented it to him in his backyard at Princeton in May 14th, 1954. And this was documented and published in the New York Times. And one fun thing is Einstein ended up donating this telescope to a youth village in Israel, and it was actually lost. And it was rediscovered by Dr. Eshel Ofer in the basement at Hebrew University, and then refurbished with support from the Meyerhoff Science Center and the Jerusalem Foundation in 2007. And it's now on display at Hebrew University. But in 2008, I got to visit this telescope in person and actually observe Venus through the eyepiece. So it's my little Einstein story. Okay, so we relatively recently had a special conference in Cambridge University. I think it was in 2019 or 18, if anyone remembers. 2018, oh, does it say? Good. 2017, okay, it was a long time ago. But it was sort of a conference in honor of Martin Rees and kind of looking at the latest in tidal disruption event observations and theory. And it really, a lot of this field got started with this seminal theoretical paper, which really set the stage for what we expect to be the observables of a star being disrupted by a black hole in the center of a galaxy. And if you read through this paper, it's really remarkable how spot on a lot of the insights were in the paper. And again, there's this famous schematic diagram of what happens to a star when it's disrupted, and the bound fraction of the debris will then fall back onto the black hole, and we get this nice, well-behaved fallback rate of the stellar debris streams around pericenter that then feed the black hole. And you see this T to the -5/3 power law. And then people often remark that the expected mass accretion rates for most black holes are expected to peak at very super Eddington rates. But in principle, we should be able to use tidal disruption events not only to light up dormant supermassive black holes lurking in the centers of galaxies, but also in principle to weigh their masses. And of course, we have this issue that once the star is disrupted and the debris streams return to pericenter, we still then have to circularize them into an accretion disk. And of course, Clement has been working very hard and others on this circularization problem. But as we have seen from the universe, somehow the gas does end up reaching to the black hole, accreting and producing luminous flares. So most recently, we have been taking advantage of this amazing capability that has emerged at optical wavelengths for these wide field, large format CCD cameras that have enabled us to take images of the night sky on relatively fast cadences over very wide areas. And we have been using these optical surveys, which have been mostly designed to study supernovae, in particular to map the expansion of the universe with type 1a supernovae. But we've actually been using this capability specifically to pinpoint transients in the nuclei of galaxies. And in fact, that is how we've been finding all of our tidal disruption events. But we've also been stumbling upon other very interesting phenomena associated with supermassive black holes. They have various names such as changing look AGN. People are now calling them ANTS, ambiguous nuclear transients. People love acronyms and various phenomena, but we're really getting exciting insights on sort of extreme ranges of accretion onto supermassive black holes and changes of state. But I do want to warn everyone in the room that although we love black holes, not every nuclear transient in a galaxy is actually associated with the central supermassive black hole. So half of our time as observers, we spend sifting out the very boring supernovae, which are exciting for others. So we work very hard to make sure that we're looking at phenomena that have to do with the central black hole and not stellar phenomena. Fortunately, as you go to other wavelengths, if you go into the X-rays and the UV, you no longer have this large contamination from supernovae. But when we're dealing with the optical, we have to be very careful. And so we use various filtering on the light curves and properties of the events to distinguish TDEs from supernovae. But we've really come a long way in our ability to identify and characterize tidal disruption events. So the first really strong candidates came from the ROSAT All-Sky survey in the 90s, from looking at archival data from the 90s. More recently, there have been candidates in the X-rays from the XMM SLU survey, and of course, I'll talk about eROSITA in a little bit. But it's really in the optical where we've been able to not only discover tidal disruption events, but produce beautiful light curves on multiple bands and then enable prompt multi-wavelength follow-up. So this has been really a game changer in understanding TDEs. Now, this sort of limits you to the TDEs that are optically bright. However, I will be showing you that we've done extensive X-ray studies of this population, and so now at least we understand their X-ray properties as well. We even have an example of a tidal disruption event that was caught in the field of view of the TESS satellite. And so we now have an overwhelmingly beautiful light curve, maybe too high of a cadence of 30 minutes, and you can see exactly how smooth these flares are in the optical. So what's really remarkable is this basic prediction for this fallback rate and power law decline of the light coming from the tidal disruption event appears to indeed be what we see for these optically bright TDEs. And another really fun observable that matches the theoretical predictions is we do see evidence for this suppression of tidal disruption events above 10 to the 8 solar masses, which is exactly what you'd expect in the presence of an event horizon, which then swallows tidal disruption events, swallows stars before they're disrupted due to the mass dependence of the tidal disruption radius. So this is a really neat result, and you can either, it's both evidence for the event horizon, but it's also clear evidence that this phenomena really is associated with the tidal disruption of stars, and it's not some continuous realm of accretion activity associated with AGN. And of course, I have Mike Kesden's plot here, where he showed that we could even use the TDE rate as a function of black hole mass, maybe to constrain the spin distribution of black holes because of how the event horizon shrinks at higher spin.
Can I ask something?
Yeah.
For the plot on the right hand side, I can imagine that if the TDE like event was detected with a mass of 10 to the 9, maybe it would be discarded as not being a TDE, so it would not show up in that.
We don't typically do that.
Okay.
Our filtering and spectroscopic classification, the host galaxy mass does not come into our filtering. It might be something that we discuss as problematic, but it doesn't go into our selection. Yeah, DJ.
Sorry, quick follow-up question on that. So I have a little bit of problem with this plot on the right, because one, the last data point has how many points? One day.
I'll show you a new one. That's even better.
The second issue is people, when they see huge flares from quasars that are 10 to the 9, they'll just throw out saying it's not a TDE, right? So because there's already a pre-cut.
So these are quiescent galaxies, true. I'm only looking at events from quiescent galaxies.
I think there is some bias in there. You don't think there's any bias in the
Let me show you the latest plot and then we can discuss. I'll talk all about host galaxies and fun things. So we really made a huge leap forward with this Zwicky Transient Facility. This survey is phenomenal because of its wide area and ability to survey thousands of square degrees. In particular, the Northern Sky Survey was generously funded by the NSF and has enabled a public survey. It is now a 2-day cadence in the GNR band, over 15,000 square degrees. This survey has been really valuable in getting the community ready to ingest transient alerts, very similar to the format of the Reuven LSST survey. So this has been really exciting capability. And it was just, NSF has just approved it for an extension into the 04 season of LIGO. So we still will have public alerts for at least another year, which is great for the community. So this is just a little gallery of galaxies that we've caught in the act of snacking on stars. And you could stare at this for a while if you wanted and just think about why are we finding TDEs in these galaxies. You can see they appear to be sort of spheroidal reddish galaxies. Here are a gallery of the light curves. This is from Yuhan Yao's most recent paper from the ZTF2 sample. And what was fun about this is we actually didn't focus a lot on the light curve shapes in this paper. I mean, she fitted the rise times and sort of half light times, you know, how long it takes to be go from half the peak light, et cetera. But you can see there's some interesting features here that are kind of, I was looking at this GS069 light curve and I heard this phrase of the second TDE, and I wanted us to make sure that we don't get too excited that there were 2 TDEs in 9 years, but was it 9 years? I forget. Yeah, but just to show you that these optically bright TDEs also show interesting structures at late times. So this is definitely a real whopper. There is a real bump. They can show plateaus. They can show sort of more broader rises and declines. Here's another sort of slight rise and decline. Here's a plateau. Here's another interesting, there's a little point here, so I'm not sure if this is an extrapolation, but there's another sort of bump there. So while initially it appears that these light curves are quite smooth, although some of them have very interesting structures, even on the peak. They do have the capability for this rebrightening at late times. And of course, we're going to hear all about the excitement in the radio. So this is something to think about. And of course, I haven't told you that we have no idea where the optical light is coming from, but I'll get to that.
Can I just
Yes.
quickly, why are these such a wide gaps in some of the light curves, in, the green one that you showed? Or,
I think seasonal observability.
oh, I see.
So, sorry, the
Yeah.
ones that show the second peak, let's say, so they're not partially, that's what you're saying.
Oh, I don't know.
They're not partial, okay.
I don't know exactly so from what so a partial disruption event, I can imagine would expect it to be less luminous, but I don't know exactly the criteria, but yeah, perhaps the secondary bumps could be, well, you tell me what they are. I don't know what they are. I'm just going to show them to you and then we can decide. Yes.
Are you going to get into, I mean, I know you said earlier that you're isolating these things to the nucleus of the galaxy, but in fact, you're isolating them to the core of the galaxy. I mean, the nucleus is not resolvable by these data. So they're consistent with being from the nucleus, but they could still be, basically extended anywhere within your seeing limit. And
Yes.
so I guess my question is, and just getting back to
Yeah.
the point you raised at the very beginning of the talk is, for the one, there's a huge range here, as you pointed out, they're not T to the minus 5/3. I mean, they don't look anything like the initial simplified theoretical predictions, but do they break up into categories or anything? Have you been able to localize them further in spatial resolution so that you really can exclude ones that just happen to be among the concentrated stellar population towards the center of the galaxy as opposed to affiliated with the nucleus?
Well, I would assume they have to be associated with the central black hole
Tell me why?
because they're not supernovae. So we can look, they're coincident with the center within our positional accuracy, which is, tenths of an arc second. However, we have done HST follow-up, for example, on the pan-stars TDE and with HST and localized it to the very center. But in general, we do all of these sources are, we follow them up with SWIFT, they're all UV bright. And they're all maintain high temperatures, and they're all inconsistent with supernovae. So they are related to phenomena within the supermassive black hole.
Right, or something we really don't know about yet.
I mean, I think they have to be powered by accretion, but we can.
Yeah. I mean, I'm not arguing,
Yeah.
I don't mean to be playing devil's advocate here. I just think.
I think the
it's still an
devil's
issue
advocate
about
would be
what's the
that they're
nucleus.
AGN phenomena. I think that's the most common devil's
That's
advocate.
certainly
It'd be
a
really
process.
hard for them to be stellar phenomena, but you can certainly try to think of some. And I'll get more to the properties of them, but I just want to say now that we have a larger sample, we now have more TDEs in these higher mass bins. And again, we see this strong suppression of the TDE rate at high masses. So I don't know if that makes you feel better.
Wait, where are the data points?
So each data point is a probability function based on the error. These are all black hole sigma relation, black hole masses. So using the scatter and the black hole sigma relation.
So there's 4 TDEs around 10 to the 8.
Yeah. And then this is a fun plot just to stare at, which I do a lot. This is now a spectroscopically complete sample of TDEs from ZTF1 and 2 from Yuhan Yao's recent paper. And what's really remarkable is the contours show you where the background galaxies lie, and the solid dots are the TDE host galaxies, and you can see that they lie very much preferentially in this green valley where where it is the least common to see a galaxy in its evolutionary state. But we are starting to see more of these TDEs in the star forming sequence. We worked very hard to get spectroscopically complete in our TDEs. And so we're now seeing more in the blue sequence, but they really are concentrated in the green valley. And for a given, like at a typical 10 to the 10 solar mass galaxy, the relative rate per galaxy of TDEs is a ratio of 1 to 2 to 0.4 from red to green to blue. So they're double the rate in the green valley compared to the red sequence, and even more common than the blue cloud, given how many galaxies are in this mass range that are blue. So this is very striking. We also, of course, have this sample of soft X-ray selected TDEs from eRosita, presented by Sazonov. And what's kind of fun is that their galaxies also seem to appear in the green valley. However, the sort of relative dearth of TDEs in the blue sequence was modeled by Roth et al. In 2021 as just due to dust. So that basically, it's not even that the flares are reddened, but they're just extincted. So you don't see them because they are very blue UV bright flares. So this is very interesting, but I do want to point out that every time you use a new method to select a phenomena, you're gonna find interesting new populations. So there's now starting to be mid-infrared selected TDEs. These are from mid-infrared emission that's dust echoing the UV bright flare from the TDE, but you don't actually see the UV emission because it's covered in, it's reprocessed by the dust, but you see the mid-infrared flare. And so there's one interesting search among WISE variable galaxies, and they found a TDE candidate that's solidly in the star forming region. And then there's this really fun recent discovery of a dust obscured TDE in our own backyard at only 42 megaparsecs. And this was completely undetected in the optical, but you see it's a very luminous mid-infrared flare detected by WISE. And this one again is in the star forming sequence.
So
Okay, so I want to ask, yes.
just out of curiosity, how are we confident that the infrared selected ones aren't supernovae? They're just too bright, too long? What's
The infrared ones, I think way too bright to be a supernova. And then, I mean, in this case, it even has T to the minus 5/3-ish decline. I think the duration also is quite long. But there's a lot of information that's hidden from you, and you basically just get the dust echo that's kind of smeared out, so you're kind of at the mercy, but they do act as nice bolometers, so you can get the total energetics of the event.
It couldn't even be like a superluminous supernova or something that's like.
I think it would be, we can check the paper, but I think it would be way too luminous. I think the peak luminosity was close to 10 to the 43 ergs per second. Okay, so now let's ask the question, TDE or not TDE? I noticed that we were talking a lot about the TDE QPE connection, maybe because they sound so similar, but I did want to point out that the QPE hosts, and you guys can correct me, the QPE experts, but they really do all show pretty strong nebular emission lines. And I'll show you in a second that most of those are consistent with the Seifert 2 So that really is indicative of ongoing accretion, past accretion activity. And maybe as we're talking about these disks that you guys want to keep colliding in, maybe we should be thinking more about not a new disk from a TDE, but a disk, a remnant disk from this past CFERT2 activity. These are what the TDE hosts look like, and they're mostly quiescent galaxy hosts. Only a few of them have nebular emission lines. So of the TDE host galaxies, only 7 of them can you even put on a BPT diagram. So most of them are just absorption feature dominated. Whereas the QPEs appear to all have the nebular emission lines, and they all seem to be pretty securely in the CFERT area region. So just something to think about, that we can't ignore, that there is this, there has to have been long-lived photoionization by an AGN. Yes.
Yeah, just a question, with regard to putting the TDE host galaxies on BPT diagram.
Yeah.
Are the lines tend to be very, very faint in TDE host galaxies. So yes, it's hard to put them on the BPT diagram if you're looking at the original spectra. I assume you're those subtracting the best fit stellar continuum to be able to detect very faint lines and measure their ratios.
Yeah.
Okay, so you're only getting 7, less than half that you could put on the BPT diagram.
Yeah, so we model the underlying galaxy light with PPXF or whatever. These are all narrow slit spectra. But most of them don't have emission lines to fit. Whereas
That's a lower fraction than we typically get once we do that. So it might be worth comparing. I don't know if it's signal to noise or if they're just a different population, which would be really interesting.
But then, I mean, just comparatively, let's say there aren't extremely faint lines that are hidden here, but they're definitely, these are much stronger emission lines. So they have different spectra.
I think it's a very different host galaxy population and in general, just in part because of the selection effect of QPEs being so nearby. So I think it's going to be very interesting. It might be an interesting possibility to try to select a subset of the TDE hosts that are consistent with the redshift and stellar mass distribution of QPEs and make that comparison. But my guess is there's still going to be a difference.
I wonder, I mean, what is the redshift range of the QPEs?
Up to 0.05.
They're only up to 0.05, they're really close. Mostly 0.1, 0.01 or 0.02.
Sorry, sorry, this is Ryan. Ryan over here. I wanted to ask quickly, the QPE folks, my understanding is there's some bias in the sense that things like GSN 069 were monitored maybe because they were AGN. So I guess we don't have to talk about this now, but I was wondering if there are selection effects that might be affecting that fraction in the QPEs. Anyways.
I think GSN 069 was a highly variable XMM, like compared to ROSAT, right?
Yeah, factor of 240 increase.
Yeah, so it was already identified from its X-ray behavior as highly variable.
I think Ricardo also had a question over Zoom.
Yeah, I hope you can hear me. I'm in plan station actually, but basically Anne commented in the way I wanted, in the sense that we should take probably the same redshift, the same stellar mass, and possibly even the same instrument, because the whole point of Thomas's paper is that compared to the spectra I take quickly for discovery, which also have weak or no narrow emission lines, once that gets you to like more refined analysis, you can see that the QP1 and 2, QP1 after subtraction is in the composite area. And if you look at the distribution of your BPT TDs, it kind of looks like the distribution of the BPT QPEs. So we might so the ones that we are able to put on that diagram, they end up in the composite and AGN area in both QPEs and TDs. And for the others, we barely see emission lines, so we can't do it at all, and we call them previously quiescent. But yeah, I think we should do like more of an homogeneous analysis in the same redshift range, stellar mass range, with the same maybe telescope ideally and the same resolution and all that. Just to get to the bottom of this question, which I do agree is very important.
Okay,
See you
yes,
guys.
yeah. Great, I agree that we should sort of. Yeah, I would say these are pretty similar analyses, but we can think about. Maybe what you guys are saying is don't get too excited that there's Seaford twos, because maybe every galaxy is a Seaford two.
That's definitely not true.
Yeah, that's definitely, okay, that's definitely true. Yeah.
Mostly liners, so.
Yeah, there are a lot, yeah, most of them are liners, yeah.
So we
Yeah,
should be comparing the top left plot with the bottom plot, right? It's the nitrogen
yeah,
tube. So statistically.
but remember I'm saying, but then there are 12 galaxies that have no emission lines at all.
So those will be some limits. Where will they be? Like,
They don't have nebular emission lines, so we can't tell, we can't decide what's photoionizing them because they.
No, but I think you could
limits.
imagine putting upper limits on the plot just to see if they
So where would they
conceivably
be?
could still be consistent, given maybe those, I'm making this up, but maybe those spectra are your worst signal to noise ones. So the ability to detect the lines happen to be the worst, and
Yeah,
that
I
would show
I
up
don't
in the
think
upper
so.
limits.
Yeah, I don't
Okay,
think this
yeah.
is.
They're all taken with KEC, your TDE spectrum.
KEC or DCT.
So obviously high signal to noise. Right? We had Magellan for the QPEs. So on the left side, they were mostly.
Yeah, I mean, you can, certainly you can. But I guess my argument would be, but these things are not like, you weren't having to dig through any noise to find those lines. I just want to make sure that those appear to have strong nebular emission lines.
So if you look at the next page,
Yeah,
you see how the subtraction makes a difference, makes the,
we do subtraction.
yeah, so but I'm saying that in our case, subtraction makes the points move.
Yeah.
If you look at QPE 1, you see how it goes from top to like bottom, depending on like I think the subtlety.
Oh,
of
so you're
subtraction.
saying when you subtract it, then it is no longer Seaford, like.
So it's
Oh.
like there is, I think that was Anne's, like Anne was the one who pointed, like,
Ah.
we have to be careful.
Well, I would trust the subtracted more. Okay, either way, sounds like, you know, we have, because we may not get a lot more QPEs, it's good to get these clues in. So one last thing about the optical, or one other thing about the optical properties is anytime we measure something, I'm always like, oh, well, does it correlate with black hole mass? So I always try to figure, you know, is there any correlation with black hole mass? Because the black hole mass is driving the tidal disruption radius, is driving the circularization timescales, all sorts of interesting things. And we do see, if you look at the black hole masses of the host galaxies based on the black hole sigma relation, we do see some correlation with the decline time scale of the TDEs, as you'd expect for the fallback, like behavior of the mass accretion rate. And perhaps we see some anti-correlation with Eddington ratio. But otherwise, there are not very strong correlations with black hole mass in the light curve properties, but you can certainly look more carefully at that. Now, we've been finding all these TDs in the optical, but we've been systematically following them up with SWIFT to get the UV properties, which we use then to get the black body luminosities and temperatures, and they're all UV bright and hot sources, and I'll show that in a second. But we also get with SWIFT the X-rays, which is really a spectacular aspect of the telescope. And so we now see that there is indeed, we're starting to detect optically selected TDEs in the X-rays. And we have 4 more from this ZTF1 paper. And I used to call all the TDEs by their Game of Thrones names. Now we have Mandalorian names, but I had personal relationships with each TDE. But this one is interesting. I made this slide well before QPEs existed. And so I did not think about QPEs, but we do have at least one example of a TDE. So the black curve shows the extremely smooth UV optical light curve. And then the purple points are the X-rays, where you can see that it appears to be flaring and then off and then flaring. And then you have an example of this late time brightening. Oh, am I out of time already?
I mean,
Oh,
we can-
no.
We have
Okay.
10 more minutes.
Okay.
Any questions, but-
This is one of the examples. Again, black is the UV optical, very smooth, and then the X-rays are initially faint, but then get much brighter. And this is reminiscent of the behavior of Assassin 15 OI, which unlike Assassin 14 LI, where the UV optical declined together, so you had a constant optical to X-ray ratio. Assassin 15 OI also initially was extremely X-ray faint, and then got brighter in the X-rays as the UV optical was declining. And so with Muriel Guolo, who's my graduate student at Johns Hopkins, he's been systematically analyzing our XMM and XRT follow-up of all 17 optically selected TDEs that were detected in the X-rays at any time. And you can see that the X-ray light curves are pretty complicated, and they're extremely soft. We very rarely get photons above 1 keV. And we have this very dramatic changes in the X-ray, the UV optical to X-ray ratio, where you can have, it can be X-rays so faint that you're 1,000 times brighter in the UV optical, and then they can approach close to 1 at later times. And because we have the XMM and XRT spectra, we can use the shape of the X-ray spectrum to get fitted with a disk, peak disk temperature, a radius. We can see how many fractions of the photons are in a corona component, what's the parallel index of that corona. And only very few, 3 of the TDEs ever show a parallel corona component. And they're always much softer than you see in normal AGN. And, but the temperatures are extremely soft, and they tend to cool a little bit with time. And we've classified these in various classes. Again, Assassin 14 LI was really unique in that it was so well behaved that the UV optical followed the X-rays. But we have now 6 examples of these late time X-ray brightening sources, which are relevant for some of the more interesting models for what's causing this X-ray delay. Is it reprocessing, or is it a delayed circularization timescale? And then we have sources that always remain X-ray faint. And then we have that one, actually this is a different one, flaring, or is it the same one? We have another flaring source. And then in this paper that Muriel is almost about to submit, we argue that when the X-ray, the optical X-ray ratio is close to 1, we end up getting radii that are consistent with a disk for the disk emission. But when they're in their X-ray faint states, you get very unrealistic, very small radii, hundredths of a and so we actually seem to think that our UV optical and X-ray spectra appear to be somewhat consistent with this unification model by Dye et al., where you have when you're looking face on, you can see the accretion disk, but when you're looking edge on, you see the X-rays are obscured, and you see mostly these reprocessed optical photons. And so this is sort of clues to what's going on with the soft X-ray evolution. And I guess I'll stop here. We have lots of interesting spectroscopy. TDEs of different spectral types, and we have clues to why. They also show interesting line shapes, and including disc-like line shapes. So all things to generate discussion, but I'll stop there.
I know it's fine.
I have a question about X-ray selected candidates from eROSITA. So we saw yesterday GSN 069 has this amazingly slowly evolving X-ray light curve where it faded by just a factor of few over 9 years. Is there any other X-ray selected TDE candidate that has a similarly slow evolution?
X-ray selected or optically?
But I think probably X-ray
X-ray
selected is the fairest since
There is-
069 was X-ray selected.
There are a couple in the literature there, and I think there's even one that's called like viscous. There's a very slow
Yeah.
X-ray selected TDE.
Yeah, there's one other one that's been published in literature where they say it's like a TDE involved from an intermediate mass black hole. But for Erisita, then the problem is that to detect like the longer timescale flares, that you'd have to do the joint analysis of Erisita with observations from X and M also. So that's not been done just yet.
There are a couple of such TDEs that evolve slowly. This is the one that we were talking about. Sorry, right, loads.
You'll share this.
Yeah, we share the screen.
So this is the one that Suvi.
Yeah,
Can you zoom in?
You zoom in.
So that still evolves. Okay, that's pretty slow. It evolves more, but that's pretty slow.
And this one's offset from the center of the galaxy. So the claim is it's a intermediate mass black hole.
Do they say something about the mass of this image?
Yeah, I mean, 9 meters, the mass estimates are few thousand, few tens of them.
More questions? So yeah,
Hi, I'm interested in more longer term evolution of optical TDEs. Some ZTF detected event was already 5 years ago. So how about the evolution? The light curve is still largely increasing or and then also radiated energy in the optical.
so there have been some studies by Van Veltzen had a late time UV study using HST and SWIFT, and he showed that many of the UV optical light curves had reached a plateau in the UV, and he attributed that to seeing the contribution from a viscously spreading disk. But basically, there are several sources that do show a plateau at late times. I don't have that plot with me here, but that, you know, several years later, you see with HST that they're still very slowly evolving in the UV. Oh.
Can I also comment, because I was on the Van Velzen paper, just that there's a lot of UV radiation coming out at late time. So it's, you know, it's equivalent of accreting 1/10 of a solar mass or something over a decade. So it seems like it partially alleviates what was earlier called this missing energy problem, that we actually do see a lot of masses is waiting, if you will, to accrete during this late, slowly evolving disk phase. That's all.
Thank you.
maybe one last
I
question.
was just gonna ask, prompted us to ask about the TDE spectra themselves and their evolution.
Oh, yeah.
Do you mind just summarizing what you found there? That's so interesting. I get more of that than the light curve evolution usually.
Yeah, so it had there was consensus in the community that there were now 3 classes of TDEs. One thing that unifies all of them is their very hot blue continuum and their lack of strong nebular emission lines. But they do show these transient, very broad features. Sometimes you just see hydrogen features. Sometimes you see hydrogen and helium-2 and these Bowen fluorescent features, O3 and M3. But depending how broad the lines are, sometimes those are blended together, but sometimes you see them very distinctly. And then you also see my favorite class, which are the helium-2 only TDEs, no broad H-alpha emission. And with ZTF, what's fun is we can now kind of look at the relative rates of these spectral classes. And we find that the TDE hydrogen plus helium are the most common. And perhaps we interpreted that they were related to the disruption of low mass stars. And to the TDE helium class remains the least common. And I still argue that they're related to the disruption of more rare helium stripped helium stars that have been stripped of their hydrogen.
Promise, come on, one really
Okay,
last
yeah.
question.
Yeah, you mentioned that for some X-ray emission, you derive a very small black body radius when the emission becomes faint.
Yes.
And then there was some you said that it favored an interpretation from a green angle. What was the argument?
Well, okay, so frustratingly, when the X-rays are faint, they don't show evidence for absorption. I mean, you don't detect any neutral hydrogen. It's just that the spectrum itself is suppressed, but they're still very soft. And so in the dye et al, they attributed this to electron scattering. So it was like a gray process that was scattering photons to lower energies. So what we're saying is that when they're in an X-ray bright phase, you can actually fit the SED with just a disk, that the X-ray to optical ratio is consistent with the disk. But when they're in the X-ray suppressed state, if you were to interpret their black body radii, you would get unphysical radii. So we think that the luminosity is being suppressed in a gray way, an energy independent way. And so you're interpreting the radius incorrectly. But maybe you guys can think of better ways to think of it. But
Great. So we'll have more time during discussion to these topics. Let's thank Suvi again.